Yes, thank you so much for having me. I'm going to be giving a talk, The Tyranny of Structurelessness, How More Meaningful Code Can Make Your Project More Resilient and Maintainable. I like to start my talks with some basic orientation, typically. So Dijkstra has this famous quote that the quality of a programmer is the opposite of the number of go-to statements that they write in their programs. But Elixir doesn't have go-tos, so why am I talking about that? So my name is Brooklyn Zelenka. You can find me pretty much everywhere on the internet as Xpeed. I'm the CTO of a company called Fission, where we're working on something called, or an idea called Web Native, which will probably not make me very many friends in this audience, because we're trying to make backends and DevOps completely obsolete by taking everything you need to build a full-featured modern web app and push it entirely into the browser so that literally your local instance is the same as production, that there's no distinction. You can kind of think of it as Phoenix Live View, but without the Phoenix part. I'm very lucky. I get to work at the intersection of all of my interests, which is programming language theory, virtual machines, and distributed systems. I was previously an Ethereum core developer, which is the world's second largest blockchain project. I no longer do anything with blockchain these days, though we're taking a lot of those lessons and applying them to things at Fission. I'm also the founder of the Vancouver Functional Programming Meetup and previously Vancouver Beam as well, though the Erlang and Elixir portion got absorbed into the more general FP Meetup. And I had also actually previously run a conference here in Vancouver a couple of years ago, and can tell you that it's a lot of effort and dedication, and you know, especially with something like COVID happening this year, I really want to thank the organizers for still making this event happen. It's not a small amount of work. I'm mostly known in this community for writing a series of libraries, the first set of which is Witchcraft Quark Algae, and there's a few others as part of this suite called the Witchcraft Suite, which is a port of the Haskell standard library into Elixir, as well as this other library, Exceptional, which I actually gave a talk on at CodeBeam Brazil a couple weeks back, which is an error handling library that I'm now taking ideas out of that and porting them into Haskell. So it kind of goes both directions. Also, when I give talks in person, I like to hand out a lot of stickers, and we make a lot of stickers at Fission. If you like any of these, including the Witchcraft one up in the top right there, or any of the others, my contact information is at the end of the presentation. More than happy to mail you some of those. So this talk, in general, is about an approach to programming, regardless of language, some observations about Elixir specifically, a vision for the future of the ecosystem. And if you were at that conference a couple of weeks ago where I spoke on Exceptional, this talk takes some of those ideas and generalizes them because it is an implementation of these ideas. And there's a couple slides in here that are about specifically, or that take lessons from Exceptional. So if you're going to take just a single idea out of this talk, it's this. It's that we should be working at a higher level, right? We shouldn't be trapped in the nitty-gritty details of how things work. We should be more concerned about what the things are. Language design reflects the intention of its creators. So very famously, Google created Go to meet its needs, right? Google is this massive company. They have said very publicly, right, that the purpose of the design of Go is to hire people straight out of university who have a C or Java background, have something very familiar to that, but without the sharp corners on it, you know, so they can make fewer mistakes, and have them be productive immediately. But this means taking the complexity out of the details and pushing them up into architecture, right? They don't have generics, they don't have, you know, protocols, you know, none of that stuff. It's very, very simple. But now you have complexity in the large. Then they can hire very well-trained, highly paid architects to break up the problems and hand out pieces, right? It works very well for them and for an organization like Google. Erlang, of course, came out of originally telecom, though it's used for many things now, but again, reflects the intended use case, right? It's really a domain-specific language for doing fault tolerance and high concurrency applications. And Elixir obviously has this Erlang lineage, but it's its own language, right? It comes out of open source, community-driven, and a lot of early people involved in the language came out of the Rails core team, and where they're taking the lessons of, well, people want systems rather than tools, right? They want a complete way of doing things and an opinionated way of doing things. If we were in person, I would take a show of hands, but historically, organizations look more like this, right? Or even Google's situation, right? Where you have one architect who breaks up a problem, hands it out to people, and then they all contribute to code. But my guess is most people at this conference, your organization looks a lot more like this, right? Where you have a bunch of different people talking to each other, handing work off to each other, and all contributing to the same project at the same time, because we need to shift what we're delivering at a higher and higher pace all the time, right? As computers get more powerful and can do more things, people want even more, right? It doesn't grow linearly, it grows exponentially, which means that the complexity of our code grows at an exponential rate. So we then run into this problem. How are we going to keep our code flexible and maintainable and easier to reason about at scale as this trend continues into the future? Do we think that the patterns we use today are the best possible patterns for software, right? Are we going to write the same code in 2025, 2030, and 2050? I would argue no, and looking back at the history of programming, this doesn't seem to be the case, right? We keep evolving the way that we do things, and it doesn't happen day to day, but it also doesn't happen in these massive shifts, right? It's this slow incremental shift. I would argue that it's not the end of this cycle, but the next step is to focus on domain and structure in our code. So I'm going to work from high level down into more specifics. So in the large, when we start programming, it tends to, whoops, went one slide too far. When we start programming, we tend to write very imperative code, right? It says, do this, then this, then this, then this. It's sort of the equivalent of saying, instead of go across the street and buy a coffee, it's, stand up, turn 70 degrees, take 10 steps, you will encounter a stair, lift your leg just so, right? And it's very clear and it's very easy to get started with because that's how a computer thinks, and we're interfacing with a computer. Most people are then introduced to this idea of functional core imperative shell, where you have most of your logic that's just transformations between kinds of data, and it's totally pure and very testable and easy, and then you wrap around it the skin that is imperative code, but it's talking to all of your pure, nicely testable, easy to reason about, understandable code. And that's mostly how people write code today. There's another pattern, I haven't invented this. This already exists, and it's called the three-layer architecture. Some people call it an object-oriented layer or a semantic domain-specific language that's specific to the kind of problem that you're trying to work on. And it's this decoupling of the data structures and imperative code, and it kind of is a bit of both, right? Here, domain, or DSL, can be anything from, if you're building a veterinary clinic, it could be about pets and their owners and the appointments that they're making. Or it could be, if you're writing a compiler, right? It could be the primitives in the language itself, right? So like there's a big span here. It depends on the kind of thing that you're working on, and they can build off of each other. But you want to have this layer in between that is, well, the kinds of things that I'm talking about are this, both data and functions, so your nouns and your verbs. That can then be abstracted away from the details and implemented in higher, higher fidelity versions. And we'll talk about this a fair bit as we go along here. The other nice thing about having this extra separation, especially if it's more structural, is we can do both property-based testing and model testing. Prop tests already exist in Elixir, which is fantastic. And it says, if we understand things about the structure of what we're trying to do, we can generate automatic test cases and not just spot test individual cases with a unit test, which then maybe there's an edge case that we're not thinking about in testing. We can just generate hundreds of thousands of cases, and maybe one of them will be will break the code. Or we can model test, which says, if I have logic or these ideas, like, I have appointments and people that can book appointments, well, I can then change out the underlying detail about that. So I don't have to actually hit the database. I can mock it out with just a map or always return the same value. And that's equally good for the test case because it doesn't matter. The semantics, the meaning is the same. And so in the context of my tests, it doesn't matter. And so our tests can become radically simpler, easier to think about. So let's go back to that original quote, "Go-to is considered harmful." What's so bad about having control? Well, let's start with what a go-to is. Not everybody knows this because they've been pretty much, unless you work directly with a virtual machine, we don't really think about them too much these days, right? So it's this low-level instruction. It's literally how the computer is still going to execute, right? The chips themselves still do this. It's very flexible because you have tons of control about where you're going to end up in the program. It's a control flow method, right? It says, well, I'm on line 6 and I want to jump to line 500, right? It's very concrete. Again, it's how the computer's going to see it. But the problem is that there's this huge number of implicit states that could happen. So here's, line 1, 2, 3, 4, 5, 6, and we, go along in order, and then we hit this line that has a go-to in it, and then we could jump literally anywhere else in the program, right? There's a huge number of places that we could end up, or jump outside of the program, right? So it's dangerous. You have a lot of control, but you may crash your program at the same time. Structured programming was considered the way around this, right? So instead of having go-tos, which are this very, very powerful but granular operator, right? We have things like loops, like while loops and for loops and subroutines, switch and branching, right? And named routines. And this was in the late 70s, early 80s, this was really, controversial. Like, why would I give up the power of being able to do all these tricky little things, right? Like you can get very efficient with go-tos, but then you have to be very careful and very clever how you use them. And structured programming at that layer has won completely, right? But we can always add more. And the trend in programming has been to add more structure over time. So the next generation here, objects, actors, protocols, map, reduce, filter for the functional programming types, functor, applicative, and monad if you're into Haskell and PureScript. Or at the far extreme of this, constraint solvers. So there's languages where you, like SQL, right? Where you say, well, I want results that look like this, figure out how to get them for me. And it will then solve, I want people between ages, 20 and 40 out of the database that also, live in Sao Paulo, right? And we don't say, go through each row and, map this thing over it. It's just, it knows how to do that for us. And that's kind of how we always want to start approaching and getting close to, is only dealing with our business logic and not with the nitty-gritty details of how, right? The trade-off here is that you're exchanging a lot of control for understanding and structure. This means that you're privileging humans over machines, or the meaning over the mechanics of how it works. And programming languages are a way of conversing with the computer. So we are limiting what we're able to do to a subset of things that we can reason about. It is safer, But if you take anything to the far extreme, so if you have things like gotos or you're working with assembly, you're in something called the Turing tar pit, right? Where you're stuck in all of this detail. The functional programming equivalent of this, using FP primitives, is called the church chasm, after Alonzo Church, where you're stuck in, well, how many layers deep of lambdas am I in? And then at the far other end is Haskell fan fiction, which you see in, yes, libraries like Witchcraft, or Scala has cats and Scalas, where it's very, very structured, but now people have to learn these extra concepts, which are very powerful, but you should have learned these things ahead of time. A lot of times when talking about these structures, people say, well, why do I have to spend this time thinking about this extra detail ahead of time and setting up the protocol and the implementation, right? I just want to write code. And the main reason is, if this is complexity on the vertical and time horizontal, there is more boilerplate to get started. But as time goes on, the unstructured version, the complexity really, because we're not thinking about it in a principled way, just really takes off, and you end up with a lot of technical debt. The structured version just completely levels out, because we know the specific things that we're talking about in our application, and things that are meaningful to us. It's much easier to extend as time goes on. We don't end up with big sections of code that are just this horrible spaghetti mess. This is the exact trade-off that people get with Elm, where, yes, there's a bit more boilerplate, but we always know how to add something more or to tweak, right? It's very structured how it works. So we're talking a lot about complexity. Let's talk about complexity a little bit more deeply. I think that the term is used in a lot of different ways, and usually it has a negative connotation. I want to change how people think about complexity a little bit. So typically when people think complexity, they think it's complicated, inconsistent, there's no plan. It's this unstructured mess that we're trying to avoid. But there's another meaning of complexity, and that's it has some deep structure, right? That we have some simple rules that can produce a lot of different results. So the Fibonacci sequence, for example, we know how to make this because it's just, take the last two in the sequence and add them together, and that's the new one. And now we can, recursively do this. And we get all of these different pictures are different versions, implementations of Fibonacci. Right? It's a simple idea expressed in many, many different ways that gives us many different results. The other way of thinking about this is, well, can we have different things that we can then stick together, right? So it's not just, in Fibonacci sequence where there's just this one algorithm that works together. Are we able to take totally separate things and apply them together? And this is called being orthogonal. So this is a picture that I find useful for explaining this. We have two lines, and we can take segments or dots on the line, and they're totally separate from each other, right? And we can think about them completely independently. Or we can attach them, and now we have a two-dimensional space. I can put a dot, we can put line segments, we can put lots of line segments, make a picture. We can add another dimension, color, and now we have color picture and time, and now we have all of computer animation from 4 basic primitives, right? So we have these 4 separate things that if we say, well, we relate them to each other in this way, we have limitless possibilities. But still, we can drop down to the layer where we say, well, let's just worry about the drawing of a single frame, or are we making sure that we're drawing the right color in this frame, right? We can pull it apart as needed and combine it, or even add more things, right? We can make this a 3D picture and so on. So complexity isn't necessarily complicated, right? Something that's complex is about its interconnected parts. A thing that's complicated is difficult to understand. Words are very, very powerful, right? So if we restrict our vocabulary, our massive space of things that we can possibly say, down to just the ones that we care about, we can introduce fewer bugs, make things that could produce bugs not possible to express in our vocabulary, right? The hard part suddenly becomes, well, what is the vocabulary that we want? And that's where we have to spend our time thinking. There's a really nice article from a couple of weeks back called "Technical Debt is Lack of Understanding." There's this historical idea that, well, over time your code will rot and then you'll have to cut it down and build sections of it again. And this article disagrees with that, right? It says, well, no, technical debt is when your code gets to the point where there's too many ideas and too many sections, and your team can't hold it all in their head at once, right? And it's too interconnected, too much spaghetti, right? And if you can keep things clear and consistent, you don't have technical debt, even as you add more features. So in Elixir, a lot of people say, well, we have actors and supervision, and we don't have to worry about bugs, and everything's really great because in the actor model, it's like an organism, and every step is very, very simple, right? I can just focus on the next step. Well, actors are, they're like an organism where every step is very simple. But organisms have lots of very simple steps that produce these very complex pictures. Reasoning about the dynamic organisms is hard, right? They're also always in motion, right? So, for example, we'll just let the process fail and it'll restart, but you may be losing messages, which in a lot of cases is fine, but in some cases it's not. So now you have to store messages for crash recovery. You have to remember to actually do that and set that up, right? The collaborator you're calling might not actually be there, right? This is all extra detail that we don't want to think about. And the complexity in such a system grows really, really fast, right? Why are we thinking about each individual connection rather than, which is in a lot of ways like a go-to, right? It's this highly detailed piece rather than talking about the ideas in our program. So let's find the common factors in them, and then that is your abstraction, right? We can pull them out into libraries, and now even your design patterns can be captured in libraries. I sometimes call that idea GenSoup because gen servers are actually pretty low level. So how do we fight the GenSoup, right? If we could add some semantics on top of GenServer, which is a really nice API for what it is, but it doesn't give you much detail beyond how things are happening. It doesn't tell you what is happening. How can we do this without reinventing the wheel every time? Is there a pattern we can apply? And we're going to look at a very common example of abstracting out something more semantic. So this is a key value database, or anything with a key value interface on it, where we can init, get, and set, right? Pretty straightforward. The simplest version of this is a map. So we can init a map, it's just an empty map. We can get and set using map.get and map.put, right? Pretty straightforward. But maps are totally synchronous. You have to hand that map around by individually, and you can't have multiple threads interacting with it at once, right? So how do we do an async version? Well, here's one where we use agent underneath. We're going to call it procdb for processDB. And this is the detail portion, right, that we're going to fit into that abstraction. So start link, get, and set, where the struct is the process ID, the PID. And then this is the implementation for the same interface, right? So init is going to create an empty procdb, right? Start link, and we're going to pass around that PID. And then get and set is, again, we're just passing around that PID wrapped in this procdb, and we can now send it messages to get and set things. So what did we get from this? Well, now we have a common interface between maps, which are synchronous, and an async procdb. We've encapsulated the detail inside of this protocol, And we don't have to think about the mechanics anymore, right? I can write code that just relies on the protocol, and we can make it synchronous or asynchronous, and we don't really care as the caller until we're actually writing an application. And at the boundary of the application, we can say, I want this to run synchronous or asynchronous. So all we have to worry about are these three functions, right? And not any of that other detail. So let's talk about domain-specific languages. These, and specifically abstraction with them, right? So these three data structures obviously have a lot of similarity, right? They basically cover the same information, right? So a list has this implicit index based on which order they're in. These aren't equally expressive. The tuple version has the most things that it can do, but also, depending on your use case, maybe some things that don't make sense, right? So if we have several zeros, well, if I expect these to be unique, then that doesn't really work for us. But all of these are covered by enumerable, or the enum module, right? And now we can abstract over all of them and talk about any enum. I want to be able to map over these and work with them in the same way. So I don't have to think about, well, how do I map over a map versus a list? My only quibble with how enum works is it'll always return you back a list, because that's part of how it works underneath. And the one plug I'm going to do here for witchcraft is witchcraft.functor has a map function that will always return you back the same kind of data structure that you've given it. So you give it a struct, it'll return a struct, a map, a list, and so on. This isn't just for data, right? This also works for functions. So here's a sequential function, right? So we're going to divide by 5, add 1, and we're splitting out and doing multiple things with the same data inside. And so we can do this sequentially or in parallel. The second par function has these asyncs on it. They're different, but they're also the same. They mean the same thing. They just go about it in a different way. Writing these two versions, there's a lot of duplicate code just to get it to be synchronous or asynchronous, when we're really expressing the same underlying idea. So also, why are we limiting this to just to two ways? These tasks.asyncs only work on a single machine. Why couldn't I imagine this was more complex, right? Why not have it on running over a cluster or over the internet, or communicating between the client and the server, right? There's a bunch of different ways that we could make this work. So, and we'll look at that specific case in a little bit. The way that we approach this is start with the overall solution looks like, right? And then choose at runtime how it's going to get run contextually. So this is always a two-phase process. We're going to make things more abstract. So we're going to start with some rough sketch, and then say, well, what's common between them? Bring that up into this abstract idea, and then bring it back down into a protocol and implementations. So basically align your ideas, figure out what the idea is, because it's often not clear at the beginning, and then we clean up the code. And then we do the concretion, i.e. we decide which option we want to actually run at the application boundary. So at the very top of the application, we say, well, I actually want it to run like this. So as a picture, you can think of it like that, where we make it more abstract and then more concrete. Can we use this to improve the standard library? Well, there's two things that we've been able to do with this, right? Fallback keys and bang functions. These are the two that I like to give a lot, and I'm still waiting for people to implement fallback keys. So if anybody wants to contribute that would be amazing. But here's the basic idea. So we want things to be modular, but that means in order to have modularity, you have to have composition. In order to have composition, you have to have orthogonality, right? So again, this idea where we have the the computer graphics, right, where we've broken it up into these different dimensions. How can we pull that idea apart, right? So let's take default values out. It's going to be very focused. It'll just do one thing. It'll work everywhere rather than on only specific functions. And we can use it in any context, right? So you can extend this and place it in any place. So this is map.get, and it has this default field at the end. Let's just remove that completely. And if I map.get with a thing that's actually the way that it's used, right, is map.get, give me b. Well, this map doesn't have that, so fall back to 4. Well, I now have to remember what that field even means, right? I've got to go into the documentation and say, well, what is that for, right? Is it add 4 to it? Oh, right, it's the fallback. So instead, we can have this fallback function where if it sees a nil, it will give you the fallback, and if it sees anything other than a nil, it will just return that value. So now we have this handy fallback function. We don't need this extra field, and it works literally everywhere. So list.first will return you a nil if there's nothing in there. Well, great. So now we can pipe this into fallback and give it this empty atom, right? So it doesn't have to be built into all of these different functions anymore. It just sticks together. So let's do the same thing, but for bang functions, right? So quick review, if you see a function that has an exclamation point at the end, it's probably going to raise. And so this is the raised version. This is an example from exceptional. So imagine that there's a version of map that doesn't do that. It just returns the struct, the exception struct itself. Well, now we have this ensure bang that takes this exception struct that's returned as a pure value, and if it sees one of those, then it will raise it. Now we don't need to have foo bang and foo, we just have the one, and if we want to make it raise, we can do that with this ensure. We can go a step further. So here's a value coming out of this safemap.fetch. And we're using this pun, this operator tilde arrow, so squiggly arrow, so that if it has an actual regular value, it will continue on. So here 1 + 1 is 2. Or if it was an exception struct, it'll skip the function on the right and just fall through and continue propagating that pure exception struct. And these are built in. There's no magic here, right? This is standard Elixir. Sorry, not the operator, the exception structs are built in. We can then put in this scarier looking version of a pipe, right, with these 3 arrows, and that will run ensure inside of it if you try to pipe it through. If you try to pipe through an exception rather than a regular value. So what have we gained from this? It works absolutely everywhere in all of your modules and all of your functions on any kind of data, on any exception struct, built-in ones or not. Your choice of flow. So we have these pipe versions, or you can use them inline, doesn't matter. It's super, super easy to test because now you can pass around these pure data structures, right? These exception structs, and it just works like regular data because it is just regular data. And as a bonus, we've fixed nil blindness, which has been called the billion-dollar mistake. So nil is very confusing because, for example, if we have a list and the first element is nil, or an empty list, and we call list.head, so we try to get the first element out, we don't know if it was empty or if it actually contained the value nil. With this style, we can have a struct called head was empty or something, and now we know exactly what happened. It's very contextual. A lesson to be learned from that specifically that I want to call out is in Elixir, pipes are very, very important. And if you can plug into the pipes, that's even better, right? So a consistent flow metaphor or punning on this works well. So we have these other, pipe-like things. The scary one is longer and more angular. And, so this top one above the thing that was highlighted is regular pipe. And now we have these squiggly pipes, which tells us, yep, I'm piping through, but it has this slightly different behavior. And this one is scary, right? When I'm teaching Elixir, pipes really make sense to people. And when I have somebody coming from Elixir into another language, their first question is, well, can I add pipes, right? So pipes, super important. If you can plug in this way, please do. So what's gained from this, right? It's super, super clear what's happening. It's composable. It works with the rest of the ecosystem, right? Very reusable. It gives the user the choice, not the library or application author, right? Or the module author, right? It pushes it down into who's calling and gives them more power. And it makes it very testable, right? You can just say, hey, is this exception an exception? And it'll tell you yes or no. And that's just built into the standard library. We could add even more to this and get even more power, but already we've made this big leap. So all of your code using these techniques can read more like a story, right? So this is Phoenix, kind of rough pseudocode, right? But on the side where we have a connection, it goes to the router, parser, model view, and then render. And we can zoom out to this high level and understand what's happening in something as complex as Phoenix, right? So using a DSL like this, right, we aren't worried about how does the router work, just that there's a router. We like to say, this is like eating the elephant, right? It's a big thing. And so how am I going to take an existing project and break it down into these parts? Well, not by feature, not by behavior. Try to see what things across those are common that you can then extract out into protocols, break up, and then re-implement and stick back in. So let's look a little bit more deeply into structure. I like to say that there's only 3 answers to any good question, right? It depends, why not both, and because math. And so in this structure, deep structure section, we're going to be focusing on the because math portion. And because math, because it's so, it's principled, it's clear, it's well-defined, right? It's things that we can understand very, very well. So here is associativity, right? It says that if I do A and B and then C, it will give me the same result as A, then B, then C, right, together. So it's not a data structure, it's not a function, right? It's something deeper. It's this interface and these rules about how things are going to work. In a picture, and notice the flow metaphor here, we're going to be using this several times for the rest of this talk. We have X, Y together and then Z, or then X and Y and Z together to give us an end result. This can be, this is called a semigroup, right? The thing that does associativity, and it has a single function called concat. And so now we can concat together integers and separately lists. And now I don't have to worry about, well, what's the right operator for the kind of data structure I'm working on? Do I have to do, map.merge or sets or, no, I just have this one concat function and it'll work for all of them. But you can't do this for any of these, right? So for example, if we're trying to do this with division, the order that we do things in, it breaks if we change the brackets. So you do have to make sure that you're doing this on something that actually means or has this property of, it's associative, right? The brackets don't matter. How do you enforce these? Well, you can, it's the structure about structures. So option 1, keep it in your brain. I would not recommend it. You can property-based test it, right? So add it to your test suite. Or part of the witchcraft suite is something called type class, which will check these for you at compile time, which does increase your compile times, but also means that you're not shipping broken code. And lets you express them in a really nice way across and make sure that anyone who implements them will have the same properties enforced. Which leads me to a quick intermission, and this is because I had to put this in here because this is like one of the main things people ask me about in Q&As after talks. So I thought I would do a little thing about this time. Let's look at how all these different things are common, right? So task async awaits, raise rescue, with blocks, SQL builders and transactions, text and JSON parsing, right? These seem very different, but it actually turns out that they're structurally very similar. So here's a function, it has input, right? And output. And then, here's a line for time, a bunch of other things will happen. But they always have this automated portion where we push out to some side effect or some side channel, right? And then, a bunch of other things may or may not happen in between. And then we have this other function where we then bring that in from this side channel and our direct, input to the function, and we continue, right? So it looks like this. All of these look like this. For example, raise, right? We end up going out to the side effect or this side channel, right? And then we skip everything in between and we come back out with the rescue. Async, we push it off, that'll run in the side channel, and we'll continue on with this main vertical column. And then later when we want that result, we can task.await it and it'll come back in. So that's the little picture of what's happening up there. So this seems to be a very real, like discovered, not invented thing, right? It's being rediscovered in lots of languages, in lots of contexts, doing lots of different things, right? This underlying structure. It models data dependencies when you have this side channel, right? When you have these effects running. These all have the same basic shape, right? Which means that we can have some deep understanding of what's happening, and we can model test them, right? So it's like we can mock out our effects without having to write effectful code if we have this understanding underneath. And it's nice to have a common interface. I don't want to have to learn all these different ways of doing things. Just give me the one way if it has this basic structure. So we'll call it a monad, right? Which is a terrible name. But people always ask, because I wrote witchcraft, right? What is a monad? And that's it. It just has this really terrible name. Even the people that created Haskell said this was our biggest mistake. We should, in fact, call it warm fuzzy thing because the name is just so scary, right? But all it is this idea that we're going to have some automated side channel that we can push and pull stuff from where it will do some stuff for us. And that's it. That's the whole idea. You've actually been using monads or monad-like things your entire career, right? The more you know. So to wrap up, we're going to do something a little bit more wild here. So we like to work with concurrency in Elixir, right? So let's make some parallel pipes, right? So instead of being sequential, they will be able to work in parallel. Concurrency is a partial order. That means some things can run at the same time, right? But because we have time, time is always moving forward, and the end result, we're just weakening an assumption, right? We're saying that, well, I don't know, which of these will run first, but at the end, they will both have run, right? So at some point, there will be an actual order that happens. So as a picture, right, here's my concurrent things, and they join together at the end. And this blue one will happen somewhere between those two dotted lines, right? Which means that the order of events might be this or one of these other two, right? So like the blue can move around in there. Which means now we have a couple ideas, right? We have serial composition, which is how we normally think about pipes, right? A, B, C, D in order. Parallel composition, where these things might happen at the same time. And we would like to not have to think about them. We're saying, well, we have this weaker assumption, so I'm going to leave it to somebody else to decide how that's going to get evaluated. So again, we have this same picture from a couple slides ago. And here's a little DSL for how that would actually work. And this is from, actually works in Witchcraft, right? And this is the picture that we're trying to say, right? So things come in from the left and they go out of the right, and top and bottom are things happening in parallel. You'll notice that it's actually even laid out roughly the same as this picture, right? So you can kind of see the picture in it. How are we actually going to do this? Well, usually at this point, people say, and then, you can just like read some docs and figure it out. Well, no, let's actually take you step by step as a way of showing how to build these DSLs and how to make your own AST. So this is the end result. This is what we want it to look like, the end cleaned up version. I'm going to split and unsplit, right? So these are things that can work in parallel or at least don't have dependencies on each other, right? It's the same stuff, just laid out in a more Elixir-friendly way. Here's the carrier data. So if you've ever worked with macros, this looks a whole lot like an AST. Here's the same functions. And here's my DSL's AST. So you're not only limited to the Beam's AST or Elixir's AST, you can make your own. This one is only about being concurrent. Or not, it just says, here's the dependencies between data, right? Well, then we can abstract it out. Here's split and unsplit, right? Or you could say non-dependency and dependency, right? Same thing. Here's my base case, which is completely sequential, right? We're not saying that this can't run in sequence. We're just saying it doesn't have to. So here's a totally sequential version. And it looks exactly like that end DSL. Here's the async version. So we'll have this carrier data called async, and we'll add to this the ability to asyncify and syncify our data. And so our data flow protocol from the top there, this lets us push things into task.asyncs about halfway down that bottom block. And now it's the same thing, except that we've added this asyncify and syncify to the top and bottom of it so that the caller can decide if they want it to be synchronous or not. And by default, it will run totally in synchronous order. This gives us a lot of meaning rather than mechanics, right? We don't have to worry about task.async or something else, right? We just say, well, these things have dependencies and these don't. It is declarative, configurable data flow that the caller can decide how they want it to work. And it's very, very extensible because it's in a protocol. We can make this work on streams. We can make this work distributed across a cluster, or you could write a version of this for something like Broadway. It's model testable. So in your tests, you can use the totally synchronous version, and it's equally applicable, right? You don't, other than testing the implementation separately, your actual code, right? The actual business logic that you're trying to do, you can do the synchronous version and it works the same way, right? And you can compose together different evaluation strategies. Say this part is going to be synchronous, this part's going to be asynchronous, and then back to synchronous again. Rob Pike, because I gave Go a little bit of a hard time earlier, this is one of the main designers of Go, said data dominates, right? If you choose the right data structure and organize things well, the algorithms become self-evident. Data structures, not algorithms, are central to programming. So I realize I'm running short on time. These are my last couple of slides. This is a call for libraries. I want people to start building things in this style so that they're more reusable, open to extension, and can run in single-threaded or distributed contexts, or in this hybrid. So railroad programming, this is with blocks, but you can do quite a lot more with them. Again, with blocks only work in one context, right? So we have our three versions here: Happy Path, the version where we're going to skip to the bottom, and then outside of this rescue block, right? We have our first one here, and then it always jumps down to the bottom, right? So this bottom section of the screen is the picture that we're making with this rescue, right? This raise rescue. We can make it explicit, we can make it generalizable, we can make it work across clusters. We can make it work in synchronous and asynchronous versions. Why can't we have a thing that we can plug into more easily, right? This would be a great library that would find a lot of use. There's a surprising number of factors in logging, especially in a asynchronous or concurrent version. And I would like to have the same interface if I'm using something like Sentry or really any logging system versus on my local machine. And my local environment shouldn't have to have some mock version of a logging system. I should be able to just log to the console and have it be equivalent, right? And a quick call out, so this is not an Elixir project. This is more in general. This is for JSON. The folks at Ink and Switch, who are doing really, really fantastic research, they have this system where we have schema versions in JSON, version 1, 2, 3, right? And they had the insight that, well, if I have a way of getting between versions A and B back and forth, and B and C back and forth, now I have a way to get from A to C or back. So if I have old code or new code running that depend on different versions of a schema, I can automatically translate between them, and I don't have to write every possible conversion. I just need people to write individual links and contribute them back. And now we have paths through different versions of schemas. This is super, super useful stuff. So in summary, use protocols to define your domain, add the semantic layer. How do you test locally your distributed system? Fire up a bunch of Docker instances. I mean, it gets really complex really fast unless you look at properties, and then you can just model test them or mock them out. Under which conditions does your code work? Do you know, right? What are your assumptions? Let's make our assumptions explicit in code. Prop test is very useful for structured abstractions. And with these things, as soon as you have a more principled, structured way of working, you should be able to code half asleep and the structure will just guide you. And to close off with 2 quick quotes, is the highest goal of programming to enable good ideas to be elegantly expressed? And give me the right word in the right accent, and I'll move the world. Thank you.
I'm giving the claps that people are sure wanted to give you from home. So yes. What an amazing talk. I mean, it was mind-blowing. It was dense. I'm absolutely sure that I'll have to watch and rewatch this at least a couple of times to absorb all of it. So thank you so much, Brooklyn. It was really amazing. So I don't even know where to start. I mean, I love the way that you put some concepts out there, like showing how, since the beginning, showing how the trade-offs change over time. So what was important back in the 80s was not the same thing in the 90s, and of course it's not the same thing today. How those trade-offs have evolved over time. It was really nice to see that. And the way you talk about decomposition and making, like, taking decomposition to the extreme and thinking about the atoms that we use to compose. So atomic functions and composing stuff from the very minimal units. That's also something that was like mind-blowing for me. And thank you for reinforcing that idea. I think that sometimes we get too carried away in our day-to-day lives, which we're working mostly with integrations and like in the outer shell, and we usually forget to take a look back into our functional core. So it was really, really nice to do this dive deep into the functional core with you. So thank you for that. It was really refreshing to see that. Sometimes we just like we get so carried away with the outer shell that we don't see those underlying structures and the stuff that we are working. So it was really, really nice to revisit that today.
Mm-hmm. Yeah. Well, thanks. And yeah, really the things that I'm trying to get across there. And mainly, yes, we get trapped in this outer layer, but if you want it to be maintainable, you have to bring it back in. So, yeah.
Exactly. Yeah. And this has a lot to do with Raquel, one of the speakers that we had today, was talking about, like, in order to make it reusable, whatever you're doing, in order to make it reusable, you have to make it small and unique in terms of responsibilities. So this was, yeah, it was really nice. It was like magic, like stuff revealing right at my face. So it was a really inspiring keynote.
Thank you. Thanks.
Yeah, we got lots of clapping action here in the comments. I don't know if we got any questions so far. Let me double check. Oh, cool. Sign patterns.
Mm-hmm. Event sourcing would be the best way to separate pure from impure code, or is a good thing to use design patterns in this case. So that is one way of doing it. Event sourcing has the nice ability that you can then replay over the events later, or if you change your model, you can then go back and replay, right? It doesn't address everything. So it doesn't address error handling or concurrency or some of those other details. But it is a really, really nice pattern, and absolutely something that we could, people when they do event sourcing tend to set it up by, well, we'll dump these into a database and then we can replay them later. And would be a nice building block to have available in general as a library, right? And there are some libraries for this, but then to say, well, which database is it going into? How am I going to run that locally? Maybe I don't want to deal with all that detail, early on, right? You can extract over that. It won't necessarily make it pure versus impure. It's just pushing events into a queue, right? So there's still a layer in there of, well, what's actually running off the event, right? So there's one more layer in there that you can abstract and test. But yeah, event sourcing is fantastic and a really nice design pattern. Yeah, absolutely.
Interesting. I've been doing lots of event sourcing recently and using broader as well. You mentioned broader in your presentation. So I just got reminded as like using broader for the first time was also mind-blowing. And I'm starting to see those patterns emerging. So that's something that is also really interesting.
Well, and I should mention, Broadway is I'm not sure if it was as intentional, but it is an implementation of these ideas where we're going to say, well, I don't want to really care about as much the details, just that it happens, right? Yes.
So RabbitMQ, SQS, whatever is like the underlying layer of messaging, it doesn't matter. So Kafka, whatever, just like come at me and I will give you this layer of abstraction that will fit your purpose. So this is awesome, amazing. Well, Caleb says thank you for your answer. Awesome. So do we have any more questions? I don't think so. Let me check.
I think we don't have it, but I have a question for my curiosity. I've been working with Elixir for 2 years, near to it, and I came from Ruby context and other imperative languages, and dive into the how to convert this, how to. I have some difficulty in how to translate all this. You present all these instructions very clear for me, but we have this abstraction, we have this idea how to do it in the code, how to start in small pieces. If you have, the question is more about if you have any suggestions about how to start it.
Yeah, absolutely. So especially people coming from an object-oriented background, there's a misconception that object-oriented and functional are opposite, and they're not, right? They're completely separate things. You can do object-oriented programming in functional programming, absolutely, right? And so part of what I'm suggesting in the talk is, well, what are the things that we can take from that are very natural in, say, Ruby, and apply them into Elixir, right? And the way that we do that is we use, instead of a class, you use a protocol, and you attach methods to data, right? So instead of having, a animal class and it has, run, right? We have a animal protocol and, run on it, and then we attach that to two different animals. It's so easy to just write a module called cat and dog, and then, separate those out. But what if we just want to have that same kind of abstraction as you had in object-oriented object-oriented programming, right? It does a really nice job of those kinds of relationships, and something that a lot of people lose as soon as they move to FP. And so having the ability to say, and which was really why OO was so popular in the early 90s, especially for graphics, was to say, well, I just have a button, and this button has some methods on it, right? And we can do the same thing. We can still create this idea of, well, here's my, in that example, UI elements, and the language that I'm going to use about it, the messages that I can talk to about it, this, whatever the underlying thing is, are these messages. And so I use some like underlying structural properties, because those are things that are good at prop testing and model testing. But typically out of those, and for libraries, you tend to work more at that layer. At your application, you tend to worry more about like, well, what are the kinds of things that exist in my vocabulary? And that's something that I see missing when I dig into a lot of FP code bases, right? That I see missing in people's projects is it's just, we get right down to, here's a bunch of gen servers and they pass messages around like this. Well, that's great, but it's very difficult to maintain in the long term when we start adding more and more of them to it. So finding the things that you can abstract out is really the first place. And I would say in an existing code base, start really high level with, here's the domain that we're working in, right? It's a healthcare provider and they have, patients and schedules. And then slowly work down from that into more connecting different parts of the code through more abstraction. And it makes it more testable, easier to extend, et cetera. But you can really work this top down. I would say start this top down rather than bottom up.
Interesting.
Yeah.
It's interesting for me, like join the two last speakers, we started talking about how to developer using the Apple, like the IX, and testing the abstractions, how to convert this idea to the code. And then it was the Medium presentation, and then Rachel starts talking about how solidity principles help us dive into translating this oriented programming language to functional programming, and now you have like joining out everything. It's very interesting for me. Thank you so much.
Oh, great! Thanks.
Yeah, I think you just.
Questions?
Yeah, I think you just automatically answer Andrew's question. So he was bringing up the topic of elevating monadic patterns to a system level. So basically what we were just talking about, going bottom up and top down. So yeah, I don't know if you have anything to add on top of that.
So I do. So specifically monadic patterns at a systems level. So at Fission, our backend is written in Haskell. So we do this pretty much constantly. There's a design pattern called tagless final, where you, so again, a monad is just something that has this extra effect in it. So you can have a database monad or I'm going to call out to the other service or whatever it is, right? And as long as they follow that picture, you can use the same interface. And so we break everything up into anything that has some effect that's going to be run, right? Into these, and then we can decide later, well, okay, I just want to stub out the database, no problem. Here's a map, and we'll just pretend that that's what's going on. I don't want to actually run logging. Cool. We'll just ignore that, and we'll give our top level carrier data just blank implementations of those things, right? So we don't work with just, well, here's just the shape and we're gonna, leave it as that. We break it out into these different capabilities, and then we make the carrier data implementation of all those different capabilities. But because they all follow that same shape, we can basically join together at each step. It's gonna run all of these together, right? So you can absolutely break it out into these individual APIs and services at the top level. And then model test it underneath or swap it out with a different implementation. So yeah, absolutely.
That makes perfect sense to me. Yeah.
Yeah.
So I think we just have 1 or 2 more questions. I think it's going to be real quick. So thinking in educational purposes, how do Haskell and Elixir would relate to each other? And
yeah, so obviously I'm a big fan of that style, and there's nothing required at the language level to do these things. I would say in general, people should learn the widest possible number of languages that they can. It gives you more perspective. So it's not just, this Haskell style, right? More people have an object-oriented background. So I have another talk from Lambda Days a couple of years back where I implement object-oriented programming in Elixir, class inheritance, messages, like the whole thing. So you can do that. Would it be worth learning Haskell or at least the basics of it? Yeah, absolutely. Do I think that some of these abstractions are really nice fits? Yes, right? Is there a bit of a design pattern that you have to learn? Sure. And are they any harder? No. It's just that people aren't as familiar with them, and you tend to pick up object-oriented patterns just because they've been more popular for longer. And you learn, factories and adapters and all of that stuff. These are also just design patterns. Are they really nice fits for functional programming and working with pure data? Yeah, absolutely. And it will clean up your code. And it does, again, in the same way that a factory is this abstraction over all of these different use cases, a functor or a monad or a semigroup are abstractions over all of these different use cases. So it gives you more tools in your toolbox, and ones that are absolutely gaining in popularity across many languages. And yeah, it really can't hurt to learn and add those.
Yeah, I already feel like trying those out like today. So to wrap it up, one final quick question is still on the education topic. So where do we start? Like, there's a lot of stuff to learn about Haskell, Elixir, functional programming overall, and we get really lost when we are starting on this journey. So if you were to give us some advice on where to start, what would you say?
Yeah, so I would say 2 things. One is, if you want to learn Haskell in particular, it's literally called the Haskell book, or I believe it's haskellbook.com. I'd say that's probably the best current resource for learning Haskell. But if you just want to learn these concepts, and in fact, where Witchcraft came from was I was running the Vancouver FP meetup, and people were really excited about learning what an applicative or a monad were, but they didn't want to have to learn yet another language. We have a lot of Rubyists in Vancouver who are interested in learning Elixir. This is maybe 2013, 2014, somewhere there. So people are learning Elixir. So I said, well, let's implement these in Elixir and make the docs basically, not exactly a course, but have explanations and diagrams and stuff. So you can look at the Witchcraft docs, start with functor, which is very close to enum, and work up from there.
Amazing. Well, I think that's a wrap. Again, I'd like to reiterate, thank you so much. We're so grateful for you being here today. It's been a long day. We had like several hours of different talks about different topics. We talked about community. We had some technical talks. We had some more people-focused talks, and it's been like a great day. And I think your keynote was a perfect one for wrapping it up. So thank you again, Brooklyn, and we'd love to welcome as a honorary member of the Brazilian Elixir community now.
Yay!
Yeah. And yeah, we would love to have you here in person next year if a vaccine is available. We're all like praying for it. Yeah.
Yes. Yeah.
And it would be great to have you here once again next year in person. So let's hope for that. So I think that's it.
Great. Thank you so much.
Thank you.